Hey there, everybody. This is Mr. Sheeline. This is going to be the video covering the 3.1 notes, the types of energy. Before we get into the notes, I just want to remind you that you should have read the instructions in the Google Classroom as far as how to take these notes. There's pretty much three different ways. The best two ways you could be taking notes is basically writing this material down. So if you've got an empty notebook that you can use that empty notebook to be writing this material down. If you have access to a printer and you're able to print this material out, awesome. Print it out, fill out the notes as we go along. And you can print that out from the student version of these notes, the PDF that I've provided you. And then the third way, which is not the most ideal way, but is still an okay way to fill out the notes, is that you can also fill the notes out using the student version of the slides where you fill in the missing material as we go through this video. I don't really recommend that one because if you've got a cell phone where you're able to listen and watch me and type at the same time, awesome. If you don't, it's going to be nearly impossible. Trying to keep this screen, small and short off to the side and then trying to type things in on Google Slides on a Chromebook is a nightmare. So I don't really recommend that version. So the best way is to write it in a notebook or to, again, if you're able to print off the student version of these and write these as we go. And scientifically and what the data shows is that writing the notes down is the best way to take notes. Fun little fact. So anyway, this set of notes is going to be pretty quick for the most part, but it is going to rely on you to know a lot of terms and to really understand those terms. And that's why I really want you to write these down, because it's just a lot of terms and a lot of examples that go with those terms. Really nothing more than that. There's no calculations or anything to that degree. So let's just get straight to it. Okay, so learning objectives. So the learning objectives for this one is pretty straightforward. I want you to be able to define the word energy. I want you to be able to differentiate between kinetic energy and potential energy. It's a common two types of very, very common types of energy used in around the world throughout all life. Everywhere there's potential and kinetic. We'll go through those and you should be able to know the difference between the two by the end of all this material. I also want you to be able to define and list the different types of energy, and I want you to be able to relate and associate the examples to all the different examples to the correct types of energy. Okay, so it is asking quite a bit, but it shouldn't be too difficult. So let's just get straight to it. Okay, so what is energy? So energy, for the most part, is the ability to do work or to produce heat, and this should be, for the most part, pretty straightforward. When we think of energy, we probably always think of like running, or we think of walking, or just eating. We think of power plants. We think of electricity. It's our ability to do a thing, or it's the ability to do a thing, because without energy, you can't do those things. Energy is transferred by a force moving an object a particular distance. And realistically speaking, what that's referring to is work. And that's just the transfer of energy. So the little guy down here, here's an applied force. So he's pulling this little box here. And as he's pulling this box, it's an example of work. He's using energy. He's using a stored energy in order to pull the box over a particular distance, and we can calculate the amount of energy used to carry that box due to the weight or the mass of the box, and for the most part, how quickly it was able to move. So anyway, brief little summary of what energy is. Okay, now here are the different types of energy that transfer back and forth to one another, and for the most part that we see in everyday life. So here's are the eight basic types or forms of energy. Other teachers, will teach even more than what I have here. Some teach fewer, and there's some scientists that argue about the different types of energy. If realistically speaking, maybe they're not too different from one another. They're too similar. Do we really want to, categorize them as two different things, etc.? But here are the eight that we'll cover. So kinetic energy, going straight to it. So we should remember a little bit about kinetic energy. This is the energy of motion. Okay, so this relies upon the speed and the mass of a particular object in order to calculate. So that's like riding a bike, that's throwing a baseball, it's like walking, swimming, typing, it's energy in motion. It's the energy in order to get to or for while something is moving. And here, like I mentioned up at the top, the mass and speed is what we use to measure the kinetic energy. And then here is the formula right here. It's that kinetic energy is equal to 1/2 times the mass times the velocity squared. Like I said before we went on break, we're not going to be able to get into the calculations of this energy, but that is the formula. So if you ever are curious on how to calculate the kinetic energy, here it is. So, and then here are two examples here. So kinetic energy of this lady swinging. So as we can see here, as she's moving her body mass back and forth, she is propelling herself on the swing. And then we're going to get to this in just a second. But then here we have kinetic energy. So maybe this is a good segue to go then into potential. So potential energy is the energy that is stored as a result of position or shape. So to kind of relate this back to this picture here we have stored energy. There's this arrow hasn't been it is not in flight yet, but there's the string that we know is storing all this energy that's going to be released and send it flying. So potential energy is that energy that's being stored, that's ready to be released. The kinetic energy is then the energy of the energy used to propel an object into motion. Okay, so let's go back to potential. So for the most part, and it's pretty easy to think. And even in this example up in the top right hand corner, here we've got a lady holding a ball, and the ball is at a particular height. And here we know that the ball has a particular mass. And so there's a potential for it to move a particular distance, and we can calculate that particular amount of energy due to that distance and due to the mass. Okay, and here she drops it, and it's being transferred from potential energy to kinetic energy. Okay, now, but there are two different kinds of potential energy. There's gravitational potential energy, which is the one that we go over, and that's referenced the most and arguably the easiest to remember. And this is the one like up here. It's where the mass, height, and the acceleration due to gravity affect and are used to calculate the potential energy. And so its formula would look like this. So potential energy is equal to mass times the acceleration due to gravity, g, times h. So this should be a familiar looking formula. We did a little bit with this before, and also the kinetic energy in that little algebra boot camp thing we did way back when. So it should look pretty familiar. And here's the gravitational potential energy. Again, we won't really be calculating this, but it's important to see and recognize the formula and to understand what components go into it, because you'll need to know these components. I'll be asking like what is it? What do we use to measure gravitational potential energy? And you got to tell me mass, height, and the acceleration due to gravity. Okay. And then as for examples are concerned, so examples would be like water behind a dam, a book on a desk, a diver standing on a diving board. It's an object or thing that's standing close to the edge of at least in these examples, close to an edge or elevated to a certain height, where when they fall, when they are plummeting, there's a particular amount of energy that's going to be released while they're falling. Okay. And then the second type is elastic potential energy. So elastic potential energy is potential energy stored in an object that is stretched or compressed. So an object's shape is changed and then returns to its resting state. So examples of this would be rubber bands, golf balls, because golf balls will expand and contract. It's really cool. There's Veritasium has a really cool video on that. And then the springs. Springs are a classic example, and one that scientists in physics use all the time, and is used, as you can think of, in automotive. It's used in, you can think of bed mattresses. You can think of In cars, you can. Well, I guess I already said that. In most mechanical manufacturing materials, springs are used. Another example would be the bow and arrow. The string on a bow is elastic energy. It's stored energy to change the shape of the string, and then it wants to revert back to its original shape. When you release the bow, when you fly the arrow, I should say, when you fly the arrow, the string will return back to its normal shape, and that energy is then released. Okay. Then there's mechanical energy. So mechanical energy is the energy associated with motion and position of everyday objects. So it's just to say that here's potential and kinetic energy, here's the sum, here's how we're going to transfer it into this action. Okay. So examples of this would be speeding trains, bouncing balls, a running person. It takes into account that at every single moment, these objects are in states of both or have a state of where they have both potential and kinetic energy at the same time and transfer to a particular kind of action. So you have the hammer here. So it's potential when you raise it up. It's kinetic when you allow it to fall. It's mechanical when it hits the nail, because that energy is transferring from the hammer to the nail in order to drive the nail into the wood. It'd be the same thing for a bow and arrow. Okay, you would pull the string back, so there's your potential. You would let the string go you let the string go, so the potential energy stored in the string then transfers into kinetic energy in the arrow, and then the mechanical energy is the arrow flying through the air to eventually hit a target, and arguably that energy would then transfer to the target and would cause it to move. It would cause it to shift. It would allow the arrow to pierce whatever the target is. Okay, so that's mechanical energy. It's pretty straightforward. It's everyday energy in the objects and tools we use. So then there's thermal. So thermal energy is the total potential and kinetic energy of all the microscopic particles in an object. So the idea is the faster atoms move, the more thermal energy an object has. And inversely, the slower the atoms move, the lower amount of thermal energy. Okay, and so thermal energy is what allows hot air balloons to function, or even blimps to for the most part to function. Molten metal, boiling water, frozen water, even the inverse of that. So hot air balloon, what allows it to fly? It's the heating of the air around the heating of the air immediately with inside the balloon, and we know that hot air rises, and so it allows the people in the basket to basically rise above the surface and to continue floating in the air. Okay, and you can even see in this little GIF over here, you see as there's like this little fire, the blue and the red represent the little atoms in the room that are bouncing off of one another. And you can see that the blue guys are colder and they're not moving as quickly as these guys here by the fire, the red guys that are have an increase of thermal energy and moving faster, and they're moving quicker, and they're moving further outside, further around in the room. Okay. Then we have chemical energy. So chemical energy is the energy stored in chemical bonds. So this is the energy that is used to hold chemical bonds together, and it is the energy released when bonds are broken. So as you can see in this GIF, so here the energy goes into breaking the bonds, and then when they bond together, there is energy that is then released when they bond. Okay. So this would be like burning wood. This would be like food. When you eat food, you're breaking down the bonds that hold the food together, that make up the food, and you use that energy to allow you to basically function. Okay. Gasoline is also a good one. So gasoline has decently easy bonds, bonds that easily break, and when they break, they release. Well, they break and then form different bonds, and those different bonds are the energy that the car basically absorbs in order to pump the pistons and to continue moving. Electrical energy. So this is the energy associated with electrical charges. So what it is that there are currents of energy, and these currents create a differential between two opposing charged objects. I'm not going to get terribly into details here, but just understand electrical energy through the ideas of, like, say, batteries, lighting, electrical components, such as the energy that comes out of outlets that allow you to power your tools and your, say, your phones or pencil sharpener or a lamp, whatever it is. It's the energy that travels through a plane in order to power another thing. We'll just call it that. Okay. There's the electromagnetic energy. So electromagnetic energy, this is energy that travels through space in the form of waves. So this is often used for communication because of the fact that they can travel long distances. And so that would be examples of, like, radio waves. So radio waves are included on here. And as you can see on both the GIF here and also this diagram here, this is what we have here. This is the different types of waves. And so as you can see in this first one, like right here, so there's line, it says line. I can't read what else it says, but here you got like radio waves. Here you've got, I think it says microwaves. I think that says microwaves, whatever it is, or infrared. No, I'm sorry, I can't really read this picture. I should have chosen a better picture. But over here you can see in the GIF, you have infrared waves, visible waves. There's X-rays, ultraviolet. Here, I think that yellow one would be getting into the radio waves. And I don't know what this green one is off the top of my head. It says line over here, but anyway, the idea being here is that energy also moves in wave form, and the wave form would be seen as, let's say, as a photon. So a photon being is light energy. It's coming from the sun. It's coming from the lights that illuminate your room, and those photons move in waves, and they bounce off of objects in wave form, and which allow you to absorb that information and all that light bouncing off all those objects in the visible spectrum. There's also ultraviolet, which gives you skin, or that can cause skin cancer because it breaks down your DNA and harms your DNA if it pierces past your melanin, all that good stuff. And then you have like X-rays that pass through your body. You've got radio waves that allow the communications. There's the microwaves that more or less are at a frequency in which it heats up water. It moves water molecules crazy fast in order to pump energy and to create heat. But there's a long line of different types of, or a range of energy here in wave spectrum in electromagnetic energy, ranging from communication to vision to say X-rays. Okay. And then finally, there's nuclear energy. So nuclear energy is the energy stored in atomic nuclei. So two examples of nuclear energy that we can harness to a certain extent. So there's nuclear fission. So this is breaking apart atoms, and this is to release, energy stored in the bonds of a nucleus. So that's what, for the most part, they do in nuclear reactors, and for the most part, what allow atomic bombs to be atomic bombs is that you split these atoms and you harness the energy and you grab the energy in those bonds to, in the case of nuclear reactors, to generate heat, to then produce steam, which then that steam turns turbines, which then those turbines rotate magnets around metal coils. Those metal coils then, for the most part, transfer the energy into electrical energy and then are pumped out to your homes. Okay. Or in the case of atomic bombs, where the energy is not harnessed, but rather allowed to expand in the form of a destructive, basically a giant destructive explosion. And then you have nuclear fusion, and this is where we fuse together nuclei. And even during the fusion of the nuclei, as we saw when we have chemical bonds, when chemical bonds fuse together, there's a release of energy. Same thing here with nuclear fission, is that when you bond atoms together or different parts of atoms together, you then release energy as well. And the great example and the best example of this is the sun. The sun is nothing more than just a giant ball of explosions all the time. hydrogen bumps into each other constantly at crazy fast rates to form helium, and then helium then leaves in different forms as either alpha particles, or it leaves. I won't get into too many details other than that, I guess. But anyway, hydrogen bonds together super quick, super fast, super hard, and creates all different types of atoms. That creates energy, and and it's usually in the form of protons, light energy that then comes down to the Earth and to all the other planets within the solar system, and allows us to live our lives pretty well. So that's nuclear fusion. So that is all the 8 types of energy that we will cover. So after you have watched this, after you now have all those notes together, make sure that you read up on all of these different types of energy, lock them down, understand them, and have a decent understanding of what they are and what the examples are for each of these different types of energy. And then after this, you have a Nearpod activity to complete to help really lock this in. So make sure you go back, read the instructions, see what you've got to do for today, see what assignment is on your to-do list, and then go complete it. Okay? So anyway, all right, guys, that's the video for today. So thank you. If you still have questions on this, make sure that you see what my office hours are so you can get a hold of me when you need to get a hold of me. Okay? So anyway, that's the end of the video. So thank you for joining me, and I will see you in the next one, my dudes. Oh, great outro.